Good morning, Integrated Math 1 students. This is Mrs. De La Rosa. Today's lesson is about tree diagrams. Why do we need tree diagrams? Well, we need trees so that we have oxygen to breathe, but in math, we need trees to help us visualize sample space, and that is all of the possible things that could happen. Wonderful handwriting here this morning. We also need trees. They can help us organize probabilities. So, especially for compound events, that is one thing happening after another, or we could even say several events. This and that happening, this or that happening. And as a quick reminder, compound events with the word and, or we call them intersections, can be calculated with multiplying probabilities, just like our area model with fractions, multiplying those fractions. Compound events with the word or, we will be adding the probabilities. So let's see how this works. We'll start with a familiar example. First, we will look at flipping two coins. The area model, as I was just alluding to, can be used to see the sample space. The first coin could be a heads or a tails. Second coin could be a heads or a tails. And then the intersection of all of those events gives us the heads, heads, tails, heads, heads, tails, and tails, tails. There are 4 outcomes. We can see these same 4 outcomes. I'll work on my handwriting here. We can see the same 4 outcomes in the tree diagram. The first coin has 2 options. Those 2 options can be labeled in our tree diagram at the end of these branches, heads or tails. The second coin, well, if the first coin was tails, the second coin could still be heads or tails, and so we will label it. If the first coin is heads, the second coin again could either be heads or tails. Every time there's a new option, the sequence of events can be shown with a new branching. So this is a sequence of 2 events because we branched twice or broke out twice, one after another. So we can still see the same outcomes. Here at this end of this branch is the heads heads option. Here at the end of this branch is the tails heads option, heads tails, and tails tails. All options are accounted for. Now here's where the probabilities come in. As we label these branches, we can label the probability of each event happening. There's a 1/2 probability of tails happening. If tails happens first, there is still a 1/2 probability of heads happening. Now that sequence of events sometimes can be changed. The next probability may be affected by the first event, but not in this case with the coin. The probability of tails is still 1/2 after a first tails occurs. And if we try to answer a question like what is the probability of 2 heads in a row, we simply multiply the probabilities along these branches. 1/2 times 1/2, for example, would be a 1/4 chance that you would get 2 tails in a row. All branches can actually be filled in with their probabilities, and in the end, for all 4 of these events, you should be able to calculate their probabilities. These, in this example, are all equally likely, so every single event, tails heads, heads heads, heads tails, will all have that 1/4 probability. For example 2, we'll be drawing without replacement. These are marbles being drawn, and if we draw them from this bag, we can show the possibilities with an area model, but it is a little bit limiting. So let's see how limiting it can be. We would almost have to draw a different area model for each circumstance. So first, if the red is drawn first, well, these are your options. We have blue, 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 red, red on the first pull. Now the second draw, this event is affected by the first draw. So again, we would have to draw another table here, area model, if the blue were drawn first, and we'll do that. But here's what happens without replacing that first red marble. We still have the 3 blue marbles, but now we only have 1 red marble. So all of the possibilities could be seen in this area model if red is drawn first. Now, it would all be different, of course, if blue were drawn first. So I would have to draw again a different area model. If blue were drawn first, we would still have these let's count 5, Mrs. D, 5 options. If blue is drawn first, then the second time we only have 2 blue and the 2 red remaining. So this would be a different table. That takes some time. That's a little bit tedious. The nice thing about tree diagrams, the one diagram can show every different hypothetical. So whether a red is drawn first or a blue is drawn first, this one tree will show us all the possibilities. After the first red is drawn, there could still be a red left and blue left. Let's look at those probabilities as we label them in this tree. So red, seeing as how there are 2 of them in this bag, there are 2 out of 5 chance to get red. Now remember, we're not replacing it. So that first ball was red. What are the chances that the second one will also be red? Well, that changes because we didn't put it back. So there's a 1 out of 4 chance now that the next one will be red. What are the chances that the next one will be blue? Well, there's still only 4 in the bag, but 3 of them are blue. So I've kind of taken account for this conditional probability, knowing that the first one was red. I can change those probabilities. Watch what happens in the other half of the tree. If the first one is blue, 3 out of 5 chance, and we don't put it back, then the second one could again be red or blue, but the chances of it being blue are different. There are only 2 out of 4 now that are blue, and 2 out of 4 left that are red. So again, this part of the tree shows us what we would have drawn in our other area model. One tree shows everything that could possibly happen. Both conditions. What if red were first? It's there. What if blue were first? It's there. So this tree diagram could be used to answer any question of multiple conditions. You don't have to draw a different area model every time here. The benefit of a tree. Speaking of benefits, let's try this first example together. We're flipping 3 coins and then we're going to answer a few questions. So this might be a good time to pause the video and see if you can label the branches of this tree. It's already been started for you. Every time it branches, remember there's a new thing happening. So here's your first coin. Here's a possible second coin, third coin. What could happen? What could happen? Pause and label the tree. Did you pause? Okay, here I'm labeling the tree. Every time we have 2 options, nothing changes with coins. They are independent events. They do not affect each other, one coin and the other. I like to be a little bit organized, so there's all my heads, tails, heads, tails, heads, tails. Now to me, a tree diagram is also fully labeled once it has its probabilities marked on the branches as well. This one's going to be a little bit boring because there's always a 1/2 chance for each outcome. Those are 1/2s if you think my handwriting is sloppy. Not really handwriting because I'm just using my fingertip here. I should get a stylus. Yeah, my wardrobe too. Okay, so what is the probability of getting all 3 heads? So that event is at the end of this branch. So we will have to have 1 heads happening, 1/2 probability, another heads happening, 1/2 probability, and another. And another. Did you hear me say and? We're going to be multiplying these probabilities. So 1/2 times 1/2 is 1/4 times 1/2 is 1/8. That would be really difficult, by the way, to draw an area model for because we'd have to go in 3 dimensions. So we have a 1/8 chance of getting all heads. We just used the tree to figure that out. The next question, if you're following along in the handout, this is on page 2. What is the probability of getting exactly 1 tail out of the 3 coins? Well, this could happen multiple ways. 1 tail out of the 3 coins, exactly 1, so not more than 1. Here is one way, heads, heads, tails. Another way is on the next branch, heads, tails, heads. This outcome here has 2 tails, so we don't want that. I think this is our only other options, tails, heads, heads. Okay, the nice thing is the branches are all completely labeled, so again, we will just have to find the probability of each outcome. Seeing as how they're all 1/2, I will do this calculation basically 3 times over and get 1/8 chance for each outcome. And that means the probability of 1 tails chance that will happen, because it could happen as heads, heads, tails, or heads, tails, heads, or tails, heads, heads, would be 3/8. I found that probability by adding the 3 probabilities. Last question, what is the probability of getting 2 or more heads out of the 3 coins? 2 or more heads. Let's see, is this 2 or more heads? No. Is this? No. 2 or more heads? No. 2 or more heads, this one would count, that's 2 heads. Does this one count? No. 2 or more heads, this one would count because it's heads, tails, heads. I think the rest of these will be good. And if it helps you to list out the outcomes, you may. We have tails, heads, heads from the bottom branches. We have heads, tails, heads. 2 or more, heads, heads, tails, and heads, heads, heads. So that would be 4/8 chance, or 1/2. Looking at every branch here again, because of the equally likely events, every outcome here has that 1/2 probability, so that's how I know each one would be a 1/8. So 1/8, 2/8, 3/8, 4/8, and that's all she writes. Please look at the next problem and start to create the branches. There are no branches provided.